We're gonna do more computer vision today. Yay! So let's talk about logistics a little bit. Let me get my little thing set up over here. So homework 1 is due tonight. We have lots of office hours today, so you guys can come by and get stuff working if it's not already. The tests are not always, perfect. So if you are like 100% sure that your code is right and you're not passing some tests for some weird floating point issues, you don't have to worry about it too much because we're going to go in and just look through people's code who doesn't pass the test and make sure that you have sort of the algorithms implemented right. And if you do, then, and if the issues are just some sort of weird floating point stuff, then you don't have to worry about it. In general, the tests are probably pretty good. So it can be hard to sort of determine if your code is actually right and the tests are wrong for some reason, or if the tests are right and you need to fix something. I'm just hoping that sort of having tests is better than not having tests, because previous versions of this class didn't give you anything, so you just had to kind of wing it. So hopefully they help you out a little bit, but they shouldn't be sort of like the only thing you guys care about. You should sort of be focused on learning the material and implementing the stuff right, and if you do, you'll probably do fine on the homeworks. So homework 2 is going to be out tomorrow, fingers crossed. Start thinking about your final project. So the last 2 weeks, we're basically not going to have any homework. It's just going to be final project stuff. You can do whatever you're kind of interested in. So start coming up with ideas now. We'll have a sort of proposal and review session in a couple weeks, basically. Once we start getting into some of the neural network stuff, because I know people are interested in all of the neural network things. So just, we want to cover some of that stuff first, so you guys kind of know what kind of applications and ideas are out there. And then, is it kind of loud? I feel like it's kind of loud. Just so you guys know what kind of ideas and stuff are out there. And then we'll have sort of a proposal session for final projects, and we can start working on some cool stuff with that. So they're not supposed to be enormous projects. It's just 2 weeks plus a little bit of exam period time or something. So just something fun and something that maybe we haven't covered in class that you're interested in doing, or if you have any research you're doing on your own and you want to include that, or just start thinking of ideas, basically. Anyone have any questions about logistics or sort of issues or anything? Ew. How do you guys feel like Mattermost is going so far? Bad. Okay. I like strong opinions. It's good. Anyone else have strong feelings about it? Yeah. The threads are fucking awful in Mattermost. I hate it so much. It was pitched to us as sort of like a Slack drop-in replacement, which is not, because threads just don't work. So if it were Slack and had real threads, it would be good. It's not. So it makes parsing through questions and answers really confusing. Yeah. Yeah, that was initially what the channels were supposed to be. I have just been answering wherever people ask questions. So I think that Mattermost probably gives us a quicker response time than anything else, but also just is totally unparsable after the fact to go back through and see what questions people asked and what the answers were. Do you guys want to move to something else? Should we just stick with Mattermost because we're already on it? Do you guys have strong opinions about things? Yeah. No, we can use, so that's one of the things we can use is have a Google group for the class. Do people like Google groups? Do you want to do that? Maybe we'll look into switching to that for the next homework. People can still use the Mattermost too if they want. That'll just kind of, yeah, having a real forum thing is probably better. Yeah. Yep. Yeah, so it can be a team project if you want to. It's not anything that I'm going to enforce. So if you want to find people to work with, I assume that you guys sort of know each other a little bit, and we have methods of communication between you guys, so you can set up things on Mattermost or in person or whatever. If you want to work by yourself, you can do that. Do people want a formal team building process, or are people fine with just kind of figuring it out on their own? I think people are usually good with figuring this stuff out on their own, but if anyone isn't, email me or whatever. All right, let's talk about what we talked about last time, because we didn't quite finish it, so we're also going to still be talking about it anyway. Let me just make sure my little, I like this little thing so much. I'm excited for it. All right, so we were talking about different ways of analyzing images, basically. And one of the things we were talking about is edges. And edges are just sort of rapid changes in this function. So we've talked about before, basically, an image you can kind of think of as a function that takes two inputs. They could be integer inputs when you're actually addressing specific pixels. We also talked about extending that to basically images as functions that take real inputs. If you just want to sort of interpolate between different pixels or look up sort of anywhere and imagine that this is a continuous function. So images are maybe these functions, and edges are sort of rapid changes in this function. And we talked about a bunch of different ways that we could take advantage of this fact to find edges. So one thing that we can do is look for, or sort of think about taking the derivative of images and using our little definition of what a derivative is, this limit of sort of looking at small changes in local areas, we can come up with a little convolutional filter that will do the right thing, that will sort of do what we want it to do in terms of looking for these edges. And we also talked about how probably with these functions, there's a lot of noise that can kind of happen in images. And one of the things we might want to do is sort of smooth out our image before we do this derivative process. And so the one way that we can do that is sort of use Gaussian smoothing. And this is where these Sobel filters that you guys are using in your homework now kind of come from, is basically doing a really small little 3x3 sort of approximation of Gaussian smoothing and then taking the derivative after doing that. And we talked about how basically, since convolutions are associative, we can rearrange these operations to basically pool them together and do the convolution, do the smoothing and derivative all in one pass, basically with a single filter. And so that's where our little Sobel filter comes from. And we also talked about basically sometimes we have some problems if we're just thinking about basically taking first derivatives, because what we really want are sort of extrema in the gradient. We want basically places where the derivative is really high or places where it's really low. And so we talked about also potentially using the second derivative instead, where what we are looking for in that case is crossings of the second derivative over 0. So basically, if the second derivative is really positive and then goes really negative, we can be pretty sure that that is a extrema in the gradient, and that constitutes some kind of an edge, probably. And so we talked about, in one dimension, we can sort of use the second derivative. In 2 dimensions, we're going to use this measure called the Laplacian. And I talked a little bit about what the Laplacian is and how it's sort of the flux of this gradient field and how it behaves sort of similarly to what the second derivative does in 1 dimension, where it's going to have this same property that it's going to cross 0 where there are edges in 2 dimensions, which is really cool. And we talked about some different filters that we could kind of construct for doing the second derivative or estimating the Laplacian of an image. So again, all of these things are sensitive to noise. Since Laplacians involve second derivatives, they're actually even more sensitive to noise than just doing gradient calculations. So we're still going to want to do some Gaussian smoothing. And we talked about this as sort of a common feature extraction technique or sort of an edge finding method, Laplacian of Gaussians, or the LOG filter. And you can get pretty good approximations of this with, basically reasonably sized kernels like 5x5, 7x7, 9x9. So that's cool. We also talked about another way of doing edge finding. We have all sorts of different methods where we can use basically Gaussian smoothing functions as a low-pass filter. Yes. And how we can subtract out different amounts of this low-pass filter to come up with edges of different frequencies. So in the simplest case, basically, you can imagine you have the initial image I, and you apply some low-pass filter to it. And all that you get sort of from this image is all of the low-frequency information. So if you take the original image and you subtract out all of the low-frequency information, what you're going to be left with is all of the high-frequency information. And then we can sort of do this with different components, different Gaussian smoothing functions, and actually get sort of bandpass filters where we can specifically target frequencies that we're interested in and then apply this difference of Gaussian filter to just pick out edges in those frequencies. So we can actually look for really fine edges all the way up to sort of large edges or sort of large-scale changes in an image, things like colors and stuff like that. And it turns out that basically when we actually do this sort of subtraction where you have a Gaussian with a larger sigma subtracts out a Gaussian of a smaller sigma, you get a filter that looks a lot like our Laplacian of Gaussians. It's not quite the same, but sort of the intuition is basically just like a lot of these edge finding methods are using some similar looking filters. And so they all sort of behave in similar manners. Question?
Why is it that it reduces components?
OK, I'm going to have to think about this for a second. Reduces components with a frequency f less. So that should probably say reduces components with frequency. Sorry, so frequency is number of oscillations per second, right? So yeah, that should probably be f greater than sigma. I think probably the slides are just wrong.
Okay, and then I guess ask, like, if you do
so let me think about this again. With a sigma of 1, you're going to get more of the high frequency information. And with a sigma of 2, you're going to be cutting more of that out, right? So you're subtracting out. We can sort of go over this after class, but I think this part makes sense. The other thing is, basically, we talked about before, like sign flips don't matter as much when we're doing a lot of this kind of processing. Basically, if you flip the sign onto this, you're going to get the same responses, but you're going to just have a different sign. So your processing can kind of take that into account. And people sort of use like both, when we talked about the Laplacian, people use sort of the positive Laplacian and the negative Laplacian. So, we can, in the end, you're going to end up with basically the same information. The way that you interpret it might have to sort of change depending on which version you're subtracting from which other one. Yeah. Good questions. Hard questions. So again, we have our sort of examples of different difference of Gaussian filters where we see that you can basically get different components in the image depending on which one you use. So starting with sort of the fine-grained information in the top left that we get from just the original image minus the low-frequency information, and then showing that we can kind of pick out specific parts of the image. So in the bottom right, we see an image that doesn't have any of like the high frequency components, any of the really fine edges, say in like the leaves and stuff, but has more of the information in terms of like what colors are changing where and things like that. So we also talked about basically if we want to find an edge, why are we messing around with all this second derivative stuff? We know how to find extrema, even if they're positive or negative. We can just sort of square them or do some kind of magnitude calculation. And this actually works pretty well, and it's often an approach that people take. But we may want more than just sort of this response map. The response map is going to tell us basically there is probably an edge in the image somewhere around this area. But what we really might want in some sort of real-world scenarios to know exactly sort of the pixel boundary that edge falls along. So we're going to have to do basically some post-processing on top of this gradient magnitude stuff. And that's where this canny edge detection thing came in. basically this pipeline for actually finding these edges and sort of creating like a line drawing of your image. And this was a pretty straightforward algorithm. The first two steps are just sort of convolutions that everyone should be pretty used to because you're doing them right now for your homework. We're going to smooth the image and calculate the gradient, so the direction of magnitude. We're going to do this non-max suppression thing that we talked about, which is going to be important for your homework this week, this coming homework, where a lot of times we are sort of looking for responses in an image, and nearby places will respond pretty similarly to each other. And what we really want is to kind of pick out the area of most response. And we want to figure out basically what are the real responses to some filter that we might be running, and what are sort of some duplicate responses or some things we can kind of throw out. So we're going to do some non-max suppression. We're going to do this thresholding process where we pick out basically strong and weak edges, and then we're going to try to figure out which edges are actually real. And just going over it quickly, you guys are all familiar with Gaussian smoothing. We're all familiar with Sobo filtering at this point. Non-max suppression is just finding sort of the real edge, and every basically strong response in this response map is going to heavily downweight responses that fall in the same direction as the gradient or in sort of the opposite direction. So getting rid of edges, or getting rid of responses that don't fall along the edge that we think exists in sort of this local area. And so with non-max suppression, we get this sort of what starts to kind of look like a line drawing. And then we have to basically get rid of some of the responses that are still probably just noise, things that are too weak, that fall under a certain threshold. Because at the end of the day, what we really want is just sort of a 1-0 labeling of like, this is an edge and this isn't an edge. And so we do that, with these two thresholds that we're going to split up these edges into basically strong edges and weak edges, and then recover sort of the final edges using this process of all of the things that we think are really strong edges, we're going to call actual edges. Anything that are weak edges, if we see them next to a strong edge, it gives you basically a little bit more information. It sort of gives you a little bit more probability that those are probably real edges. So if we have a weak edge and we see it near some strong edges, then we're going to basically add it into our edge set. And then we're done. We basically have sort of the whole canny process where we can go from our image to the edges associated with that image. Yeah? Yeah. Yeah, so there are a bunch of different ways of doing this. So one, basically like the easy way of doing it is just saying like every weak edge, look in this small border and see if there are any strong edges. Another thing you can imagine doing is like if there's a weak edge and it's next to another weak edge that's next to a strong edge, maybe that's all sort of a continuation of the same line, and maybe you should include that. So people have come up with different sort of extensions to canny edge detection that take some of that information into account. These are all just kind of heuristics, so there's no necessarily like right, in the same way that there's no like right edges in this image. You can imagine like a bunch of different people, if you gave them this image to sort of trace out, they would all come up with different kind of tracings. It's sort of the same thing here, is that there's different ways of sort of processing this image depending on what you're kind of going for. So something like what you're talking about might be a little bit more accurate in terms of what humans would expect. Or maybe a bunch of weak edges that all still are connected together and form one really long edge should actually be a strong edge, even if they don't have basically a very high response. There's a bunch of ways that you could imagine kind of coming up with different heuristics for this. People sort of get canny edge detection. It kind of makes sense, this process. Yeah, people like it. Cool. We're going to keep talking about features today. I skipped some of the stuff we talked about last time because we're just going to talk about it again. We're going to talk some more about features and sort of finding interesting places in images. And then we're going to talk about this panorama stitching thing that we probably want to be doing. If we have a couple images that we think are probably related to each other, maybe we want to merge them into one image. Nowadays, your phone can just kind of do this, so it's sort of less applicable. But it's still an interesting process to talk about. And some of the techniques that we get from it, namely this RANSAC algorithm, are really cool and really useful much more broadly than just in panorama stitching. They're really good sort of estimators when you have a lot of noisy data. So let's get into it. So we talked about features basically as being highly descriptive places in images or highly descriptive sort of regions in images or something that you can extract out of the image that might be useful for something that you want to accomplish with the image. And things that you might want to accomplish are, if you have two images and you want to make a panorama, you have to kind of match up correspondences. Other things that might be useful are basically like performing recognition on an image, like figuring out what is in the image or detection, where is stuff in the image, what kind of things are going on in the image. So features are, a really big sort of part of computer vision and a really important step in terms of how we're going to process these images. And so we'll be talking about features basically a bunch. Right now, we're going to basically be focusing on this one subproblem because it's a good introduction to sort of a lot of different concepts in this space of stitching together panoramas. So we have a couple images, and we basically want to merge them into a single image. And there's going to be a few steps in this process. Basically, we want to find sort of these regions of interest. We want to figure out where their corresponding points are in the other image, match them up, and sort of blend the two images together. But when we're talking about features, sort of what we want are patches in this image that are going to kind of be unique. We basically want areas of the image where we can, if you're a human and you're doing this process, you sort of do it naturally, right? You look for areas that you can align really easily with places in the other image that make it easy to kind of stitch these two images together. So we want something that basically you can look at a small region, and you're not going to mistake it for any other regions in the other image, and you're going to be able to find it, if it exists in the image that you want to stitch together. So we talked about, basically what we want is some kind of unique patches where they're only going to match to one other spot in the other image, and they'll only match if it's actually the right location, basically. It's actually, the same place if we're talking about images, or it's actually, the same set of pixels. And one way we can kind of measure, how close two patches are from each other in images is using this sum squared difference. So this calculation, if we think about it, is just going to kind of help us in determining what we mean when we sort of talk about unique patches in an image. So, for example, if we're looking at this image, the sky is not going to be a very unique patch. There's very little variation in the sky. It would be really hard to basically take any part of this like large blue expanse and find the large blue expanse in the other image that kind of matches up with it. So it's going to have a really low distance with a bunch of other patches in the other image. So it's not going to be very good for matching these images together. And we also talked about how edges, we start to get a little bit more information, but the variation is sort of only in one direction. So this kind of patch will match pretty highly. It'll have low distance with other patches that fall along the same edge, basically. And this might not necessarily be good because we could get, some rough estimate in the other image of where this patch matches, but it wouldn't be one specific location. It would kind of be anywhere along what might be sort of a fairly long edge. And we talked about what we, probably really want is some sort of notion of these corners, where if you kind of move this patch in any direction, it doesn't really match up very well with the corner. But if you have it sort of centered right on top of the corner, it's going to have a really good match. It's going to have really low distance. So we talked about basically what you'd really want if you were doing sort of panorama stitching in a big scenario, in like a big setting, where you kind of the ideal situation is you find a patch that has a really high distance from every other patch and every other image that you can find, and the only thing that it matches up with, is the actual correct location, either in this image that you're looking at or in another image that has the same set of pixels. So that's kind of our ideal thing, but it turns out that that's really hard to do. So one thing you could imagine doing instead of that is just saying, OK, let's just look in this same image and look for places that match this pixel, or these pixel values. And basically, if a patch is sort of unique within an image, we can start to kind of get a sense that maybe it's a pretty good patch to use. You're not looking at every other image, but you can at least look just within the same image and say, okay, this patch has a pretty high distance from every other patch, except for the one that it matches with. So maybe it's a pretty good, unique sort of feature for matching up these panoramas. Now this is still pretty hard, because if you imagine, you have this some 1,000 by some other 1,000 pixel picture, and you might be looking at patches that are like 7 by 7 or 5 by 5 or something, and it's going to be this crazy n-squared computation where you're going to try to match up every patch with every other patch, and n is going to be really big. And this sounds like a really hard computation to do when we're just trying to stitch together panoramas. So instead of that, we thought, let's approximate this even more. Let's just say, how well does an image patch match up with itself? And so obviously, if you just stick an image patch right on top of itself, it's going to have a really high match. It's going to have really low distance from itself. It's going to be 0 because all the pixels are going to be the same. So really, we're just going to shift the patch around, by some small amount, basically, and see what that distance ends up being if you sum over all of these possible small shifts. And this is some sort of method of self-similarity or self-distance metric. And we see that, with these 3 examples that I kind of picked out, if we just are looking at self-difference, it works pretty well. If we look at the sky and we measure its difference with itself, it has very low self-difference. It's very highly self-similar. So even if you shift it by pretty significant amounts, it's all blue. It's all going to match really highly. Again, we have this edge where basically if you shift in directions that are perpendicular to the edge, you're going to have some increase in this self-difference. You're going to have like a little bit of self-difference along one sort of path that you might shift, but along the path where basically you're shifting parallel to this edge, you're still going to have a lot of these pixels end up matching up. So basically anywhere where you're shifting it kind of in this dimension, you have all of the snow still overlaps and all of the background still overlaps along this edge. And your distance function is going to be really low, so it's still not going to have a very high self-difference. And we saw that with these corners, or sort of generalizing basically to highly textured areas in general, but especially with corners, it makes a lot of sense, where basically you have 2 really strong edges. And what ends up happening is, we saw that if we shift perpendicular to an edge, the distance function starts getting larger. So if you have 2 edges and they're sort of, they're not parallel to each other, basically, as soon as you start shifting this image patch, you're going to have one of the edges start to move away from the other, and you're going to have some increase in your distance function. And that's what we see here, basically. In any direction that we start shifting this image patch, we're going to get some of the mountain that starts overlapping some of the sky, and we're going to get an increase in our distance function. So this patch in general has actually a pretty high self-difference. So this is the kind of image patch that we would like to use for doing this matching process. And it would probably work pretty well. So again, we can kind of graph out what happens when we're looking at this self-difference thing. And in particular, we can look at basically this distance function as relative to how much we're shifting the image in each direction. And we see that basically with our corner, our self-difference function, or our distance function is basically 0 right when it overlaps exactly where it should. And it starts getting high pretty quickly as you shift in sort of any direction. Whereas this edge has this one kind of axis running through it where the distance function is low sort of the whole time. And even though it gets high when you shift in other directions, it's low enough there that it's going to have a lower self-difference than our corner. And sort of our sky, basically, if you shift it in any direction, the distance is going to be pretty low. Do people kind of understand? This is not super complex, so people sort of understand what's going on with the self-difference thing. Yeah? Yeah. We're not actually going to end up calculating this at all, basically. So you don't have to worry about it too much. You could imagine 2 different ways, right? One thing is you could just only look at the pixels that actually end up overlapping. So you could just calculate it basically within this square and ignore all of the stuff that falls outside. And then just average, take an average over the number of pixels that fall within. Or you could imagine actually just like looking at all of the pixels, because there are some pixels outside of that, even though we're just looking at the patch. It's going to end up not mattering because we're going to make one more approximation, basically. So again, even if we were just looking at this self-difference thing and we're just doing these small shifts of every patch, we still have just a ton of different patches to evaluate in the image. And this ends up still being like pretty computationally expensive. So we're going to make one further approximation to this self-difference and come up with a way of basically estimating how self-different a patch is by just looking at sort of local information to that patch. So what we're going to end up doing is, again, it all comes back to taking derivatives at some point. We're going to be looking at the gradients in the image. And there's some pretty easy intuition for this stuff. If the gradients are mostly 0, there's not a lot of changes going on in the image. So it probably has a pretty low self-difference. If the gradients are mostly in one direction, then there's probably some kind of edge there. And we talked about how edges are OK in some sense for doing this matching, but they're going to be sort of bad because they match with themselves if you shift basically parallel to that edge. So what we're really looking for are patches that have strong gradients in more than one direction, in sort of like two directions. And if a gradient has strong, or if an image patch has gradients in two different directions, we can be pretty sure that this is some kind of corner in the image, and we can sort of think that probably that patch is pretty good. So how do we end up going about this process? We're going to basically be using sort of these eigenvectors and eigenvalues, and you guys are pretty familiar with linear algebra, right? So what we use is this structure matrix. And the structure matrix is, for every patch, going to be giving you some summary information about the gradients in that patch. So really what we end up doing is actually, at every pixel, we calculate a structure matrix for that pixel. And that structure matrix will take into account information about the gradient at that pixel, and also at the pixels that are sort of pretty nearby it, that fall within some range. And you can kind of tune how big that range is. So this structure matrix looks sort of complicated, but it's actually not too bad. What it actually is basically a weighted sum of nearby gradient information. So in particular, we're looking at some area near our pixel, some basically area I, and we're going to sum over this I, and we're going to do this weighted sum and just multiply it by the gradient information at the surrounding sort of nearby pixels. And there's a bunch of kind of math that goes into why this structure matrix is interesting. But basically, it ends up summarizing the distribution of nearby gradients. And in particular, the eigenvalues and eigenvectors can help us figure out the directions of the gradients of these nearby pixels. And what's cool about doing this sort of formulation of this structure matrix is you'll notice it's basically just this weighted sum of this gradient information at specific pixels. So we've talked a lot about doing weighted sums in this class already. A Gaussian is just a weighted sum of basically some nearby pixels. And we've also talked about doing gradient calculations. So there's a pretty easy way to sort of calculate this structure matrix. All that we're going to do is basically calculate some gradient information for the entire image. So every pixel is going to store its own gradient information. And then if we take a Gaussian smoothing of that gradient information, what we end up doing is just a weighted sum of nearby gradients with each other. So if you kind of set up basically these gradient images correctly, so basically you're going to need 3 different images. You need one image that stores basically the x gradient squared. You need one image that stores the y gradient squared, or sort of one channel of the image. And you need another channel of the image that stores the x gradient times the y gradient. And then you can end up just basically using Gaussian smoothing over this sort of structure matrix image to calculate the full structure matrix just kind of all at once. And it's pretty easy and sort of a cool process. But basically, there's some math behind this structure matrix that tells us that the eigenvectors and eigenvalues summarize the gradient information that we're encoding with this matrix. And in particular, the eigenvectors will tell us what direction these gradients are in. And the eigenvalues will tell us how strong those gradients are. So what we want are patches where the eigenvalues are basically both large. If we have two eigenvalues of this structure matrix that are both pretty small, then we know there's not really any gradients in any of the surrounding pixels. And we know that if one of the eigenvalues is really large, but one of them is sort of a 0, you're in an area that has one basically large gradient, or sort of so remember that eigenvectors and eigenvalues basically summarize the directions of largest change in sort of a data set or sort of a matrix. So we end up summarizing basically what directions have the largest variance in this gradient information, and how much those gradients, basically how strongly it varies in that direction. So what we really want are basically structure matrices that have really high eigenvalues for both of their eigenvalues. And this is just a 2x2 matrix, so it's only going to have 2 eigenvectors and 2 eigenvalues. So we want both of those eigenvalues to be large, because that means we have basically an image patch that has 2 strong gradients. And it's probably some sort of corner, and we like corners. They're good. People kind of getting the structure matrix stuff and why it might be important. If you're really interested in sort of the math that goes into this estimate and why these structure matrices actually make sense, it's all in sort of the Sliski textbook. We're not going to go over it in fine detail because it's not super important. Yeah?
You said you had one of these for each pixel?
Yep, okay. Exactly. So at every pixel, we're going to be estimating, if you had an image patch that was centered at that pixel, how good is that image patch? How good is the self-similarity or self-difference of that image patch? So, we have this 2x2 matrix that's summarizing this gradient information. And what we want to do is figure out what these eigenvalues are so we can find places in the image where there are 2 large eigenvalues. But taking the eigenvalue of this 2x2 matrix, again, for every point in the image might be sort of computationally complex. So we're going to use just an easy method of estimating the smallest eigenvalue. Because, again, remember that you have 2 eigenvalues, and one of them is always going to be smaller than the other one. The eigenvalues basically tell you the 2 directions along which your data varies the most. So the second one is always going to be the smaller of the 2 eigenvalues. So what we really want is basically this second eigenvalue to be large. And we also know that, just from our linear algebra, we have some properties about the determinant and the trace of this structure matrix, or sort of the determinant and trace of any matrix. And what these properties are is that the determinant of a matrix is just all of the eigenvalues multiplied together, and the trace of the matrix is all of the eigenvalues added together. And this actually means that we can pretty easily come up with ways, because the determinant of a matrix, especially a 2x2 matrix, is super easy to calculate. And the trace, you just add up all of the elements of the matrix, so that's easy to calculate. So we can calculate the determinant and trace really easily, and we don't actually have to look at the eigenvalues. We can just look at these summary statistics, basically, to find places where we are pretty confident that both of the eigenvalues are going to be large. And there are a couple different heuristics for making this happen. Basically, in one, you can take the determinant and subtract off this scalar multiple of the trace squared. And that scalar multiple alpha usually is very small. It ends up being like, I think they use like 0.04 to 0.06 or something. And in the other version, you basically take the determinant over the trace. And that's the same thing as taking the eigenvalues multiplied together divided by the eigenvalues summed up. And it's pretty easy to see that basically both of these estimates, if they're very high, will imply basically that the second eigenvalue is pretty large compared to other places in the image. So we're going to look for places where basically these, one of these two estimates, or some other way of estimating that the second eigenvalue is large, we're going to look for places where that is high in the image. And if it is, we can be pretty confident that there are these gradients in a couple different directions. And so it probably is an area with pretty high self-difference or low self-similarity, and that's good. So what we sort of summarized here is the Harris corner detector, which is this algorithm from, I don't know, a while ago by presumably some dude named Harris, where we're going to calculate these derivatives, which we already know how to do using our Sobel filters. And we're going to calculate these three measures, basically the x direction squared, the gradient in the y direction squared, and the gradient in the two directions multiplied together. And then we need to calculate this structure matrix. And the structure matrix is just this weighted sum. So we can pretty easily calculate basically the weighted sum for each of these three channels. And then the structure matrix is just some combination basically of those three channels. So finally, we can basically estimate our response based on the structure matrix and these approximations of the smallest eigenvalue that we talked about. And we're going to get some kind of response map, basically, of what pixels in the image do we think are centered at a region in the image that has very high self-difference, that would make basically a good patch to try to match with other patches in the other image. And then we're going to do this sort of non-max suppression that we talked about, just like our canny edge detector. And so when we run it in process, you guys can't see this at all. So if we zoom in a little bit, we end up getting some sort of things that make sense in terms of what responses end up pretty high with this Harris corner detector. So in particular, look at this little corner right here. We have this really strong gradient in this direction and this really strong gradient in this direction. This kind of makes sense. Also, this little patch right here, we have some gradient here and we have some gradient here. That looks like a nice little corner. It ends up basically picking out a lot of little corners. Here's another one where you have snow kind of in this direction and this edge kind of in this direction. So it ends up picking up a lot of these highly textured areas or these corners in the image that maybe fall along like snow mountain boundaries or sort of stuff like that. This is with the threshold set pretty low, so it's got a lot of different responses. So not all of these are like really strong responses, but it's picking up a lot of basically good features in the image or a lot of good corners. So that's cool. So now, we've run our corner detector and we've gotten a bunch of different corners for maybe a couple images. And we actually have to start doing some stuff with this. And in particular, we want to figure out some way to map from these two images to each other. So in general, we sort of have to figure out what kind of different transforms make sense to do between two images, and how we sort of parameterize these transforms. And then given a set of matches, how can we kind of solve for what the specific transform is in this case? And this is kind of a lot to think about and talk about, so just going to get into it. The first thing that we have to basically do is if we have a set of corners for two images, we need some way of figuring out what the matches are between the two images. And there are a bunch of different ways to do this. But in general, we're going to basically try to summarize the information contained in some image patch. And that summary can be really simple. And these are just sort of called descriptors. This is often what people talk about when they talk about features, are basically ways of describing small parts of an image so that you can start doing something with those image patches. So one thing that you can imagine doing with an image patch is a way to describe it is just the pixels in that patch. And this is what we've already been kind of talking about, especially with this self-similarity thing that we were talking about and this distance metric. And then if we just want to find matching patches, if all we're using is pixel information, we can just calculate this distance function between all of our different corners that we've detected, for example. So, if you look at these two images, you can imagine that basically matching up all of the possible patches, all of the 7x7 windows in this image, with all of the 7x7 windows in this image, that's a lot of work and that's a lot of computation. But if you're just looking at some really small subset, so some number of corners, this image has, I think, 50 corners or 100 corners labeled, and this one has 100 labeled. That's a lot less than sort of the 1,000 by 1,000 patches that we were talking about before. So we've reduced the space from maybe 1 million interesting kind of points in an image to maybe 100. And then we can actually just do this comparison where we look at every possible match between the two images. So if we use this descriptor where we're just using pixel values, and there's basically not a lot of variation going on in the image, this can work pretty well. We're just going to basically take the distance of every sort of interesting patch that we've already found in one image and look at every interesting patch that we found in the other image. And if that distance function is low, we're going to say that is probably a match. And in particular, we're just going to look for the lowest distance that in between the two images. So who can think of some problems if we're just using kind of pixel level information for doing these descriptors, for doing these matches? Anyone have any problems that might come up? Yeah, definitely. So, one thing that can happen is basically you're taking a panorama and one picture you're like looking right into the sun, and the next picture you are moved over a little bit, and all of the parameters of your camera are going to change, right? So you're going to change your exposure and your, f-stop, or I don't know what all of aperture, all of the different camera things. And so two patches that are of the exact same place in two different images might visually, like on a pixel level, appear totally different. So that could be different lighting, it could be different color, things like that. In what sense do you mean keep track of, I guess?
Like in memory?
Yeah. Well, you'll find out tomorrow when you start working on your homework, because you'll have to do it. But you can just keep like a list around, right? Like you just have a list of a bunch of, so for the homework, I think you have a list of a bunch of indexes and a floating point vector, basically. So you have this structure that holds basically the index that corresponds to the pixel in the image of that patch. And then you have some vector that stores your descriptor. And again, this descriptor can kind of be anything. Usually it's a bunch of floats, so that's what it is right now. But you can imagine a bunch of different ways of doing this. Yeah, absolutely, definitely. So that would be a big problem. And that might even start to just be a problem in general with doing kind of matching in panoramas, is basically if you have a lot of repeating patterns, you're going to get, if you tried to take a panorama of wallpaper, there would be a lot of matches that wouldn't necessarily correspond to the right transform that you actually ended up doing. So repeating patterns are definitely a problem. That might not even be a problem with sort of this pixel level descriptor that we're using. That might just be a problem with kind of panorama matching in general, is matching up two images that have this kind of repeating pattern. And that's when you can start taking into account other information that you might have. Things like, when you're doing it with a camera, it can actually just look at the motion that you're doing and then use that as sort of extra input when it's doing this stitching process. Because it sort of knows like, oh, he is moving the camera, but also moving it up and down and kind of stabilize that motion and do all of these interesting things when you have some extra sources of information. So the last thing that can happen is just transformations between these two images that you might not expect. So, imagine basically that you move the camera a little bit while you're taking these two images, and one of them ends up sort of significantly rotated. If you're just kind of using pixel level information, now we have these two patches that are extracted from the same place. So these two patches come from the same sort of physical location, but they end up looking totally different if we're just looking at this pixel level information, and that could kind of be a problem. So in general, pixel level information can work with some amount of transformation between the images, but it doesn't work when you have, for example, really large rotations, or if you have changes in lighting or changes in color. You can even see, even in this one, we have a little bit of change of color. I think one of these ends up being like a little bit more blue than the other one or something. So just something to start thinking about, especially as you're moving into this homework, is how do you want to describe this local region so that you can easily match it with other regions in the other image that it sort of should match with, but not match it by mistake with some wrong piece in the other image. But we're just going to use pixels for right now moving forward, and then we'll worry about other methods of feature extraction later. So gradients are just, these descriptors can be more complex. Oftentimes, good things to use are things like gradient information that doesn't necessarily depend on things like different changes in lighting or changes in color, stuff like that. You can also basically normalize that gradient information so that it becomes rotation invariant. Interesting things to consider are basically how big do you want this image patch to be? Basically, we're looking at individual pixels in terms of response to this corner detector function, but then you can imagine basically using some large image patch to do this matching, or some really small image patch. Depending on your application, all of these things can kind of be tuned. But let's imagine that we have these good corners, or these good patches in each of these images, and we have some descriptor, and we're going to go through this process of matching up the descriptors with each other. And what we might end up with is some crazy mess of matches that looks like this. And again, this is a complex problem, right? Because really, when you think about it, and this is a pretty nice panorama because we have a pretty large region of overlap. Basically, all of this part of the image is contained in all of this part of the image. So we don't have a lot of each image that doesn't have sort of a corresponding part in the other image, which makes it a little bit easier in terms of doing this matching and figuring out these correspondences. But when you're actually stitching together panoramas, what you really want is a bigger picture, so you don't want that much overlap between your two pictures. You basically want just enough overlap that you can end up doing this stitching and having it work reasonably well. So our corner detector doesn't really know a lot about the degree of overlap between these two images. It's just going to look for good corners. And then our matcher is just going to sort of find different patches in the image that match up with each other. And what you end up getting is basically a very noisy set of matches where a lot of them correspond to basically the right thing. And we can kind of see there's this triangle here that ends up matching pretty nicely to the same triangle in the other image. But then there are these two other kind of lines that are coming in to go to the same triangle that maybe it thinks also have a pretty good match in the first image. So we need to take this sort of mess of matches and figure out what the actual transform was to get from one image to another so we can composite them into basically the same image. And in general, there are a bunch of different ways that we can warp one image into another image. And we're going to end up with sort of this nested hierarchy of transformations. And it's going to require basically some new notation to talk about this math. So in general, we talk about x, sort of the vector x, as being a point in our image at the coordinate xy. And in matrix terms, this is just going to be a column matrix. It's sort of a 2x1 matrix that has the components xy just kind of stacked on top of each other. And we say that if we want to map to a new coordinate system, in general, we're just going to kind of use matrix operations to do this mapping. So given a point x, we want to map to some new point, x prime. And that's just going to be this matrix multiplication, where we take some transformation m, and we multiply x by m. And that will map to a new point in our new coordinate system, x prime. So we can imagine basically, if you think about these two images as having their own coordinate systems, both of them start at 0, 0 in the top left of the image. And both of them have their own sort of x and y components. And what we really want is to map from one coordinate system into the other coordinate system. Because if we have a mapping that works like that, then we can just look at all of the pixels in one image, map them over to the other image, and then just draw them there. And we'll get a decently good compositing. And there'll still be some post-processing that we have to do, basically. But we have to figure out this transformation to be able to do that mapping. So scaling is a pretty easy transformation to do just given these matrix operations. Basically, it's just this scalar multiple of an identity matrix where you have S in the top left and bottom right. And actually performing this multiplication is pretty easy. You can imagine just like it's going to end up being S times X plus 0 times Y, which is just S times X. And then it's going to be 0 times X plus S times Y. So all we're doing is basically scaling the two X and Y coordinates to get our X prime. But then if you start thinking about translation, things become a little bit more tricky, right? So if you want to move from X to X prime by some dx and dy, how do we pick this transformation matrix M? Because using just this matrix multiplication, all we can really do is sort of add together multiples of X and Y. And there's not an easy way to kind of use just this simple matrix. So we're just going to add a new component to our coordinate system. And we're going to start talking about X bar, where X bar is basically just X, but with this added 1 at the bottom. And this is just sort of called our augmented vector, or our augmented coordinate. And this makes translation super easy now. So if we want to do translation, all we can do is use this little translation matrix sort of smashed together with an identity matrix. And then when we do this matrix multiplication, the components of this matrix T will end up multiplying by this constant factor. And so they just get kind of added on to these coordinates. And just brief review, I is the identity matrix. And in general, we're just going to kind of use I as like, this is a matrix that sort of fits in this location, scaled by however much it kind of needs to. So it might be like a 2 by 2 or a 3 by 3 matrix. I think in this case, it's 2 by 2 identity. So when we expand this out, we have this I matrix here, and we have our translation vector T here. And again, the math for figuring out X prime is pretty easy, right? It's going to be X plus 0y plus dx. And for y prime, it's going to be 0x plus 1y plus dy. So we end up getting a pretty easy translation between image coordinates if we just kind of add on this extra little coordinate to our initial point x. So we're going to use this x bar. That's cool. That's nice. Translation will get you somewhere in panoramas. You can imagine, if you're like taking a panorama of a wall and you like take a picture and then you just move very carefully and take another picture and then move very carefully, take another picture. That's going to kind of just be a translation that you want to end up doing between these two images or between these multiple images. So all you would have to do is sort of solve for these two variables, dx and dy. But in practice, we're going to end up wanting something more complicated. So we'll sort of keep going with these nested transformations that we can do. Euclidean is sort of the next transformation that people talk about, where we're going to do translation and rotation at the same time. And it still ends up being just sort of this matrix operation. And in particular, it's going to be, instead of the identity matrix here, it's going to be this rotation matrix squashed together with the same translation matrix that we had before. And that's how we're going to get from x bar to x prime. And this rotation matrix, in particular, encodes some angle theta. And it just uses sines and cosines as the components of that rotation matrix. And I'll leave it as an exercise for you guys to figure out basically when you multiply that rotation matrix by some xy coordinate, why that ends up rotating it around the origin. So when we basically expand this all out, again, we can calculate our components of x prime pretty easily. X prime is basically going to be cosine theta times x minus sine theta times y plus dx. And y prime is going to be sine theta x plus cosine theta y plus dy. Still, pretty easy matrix operation. And this is cool. We're already doing rotation and translation kind of in the same operation. It's exciting. We have more things we might want to do. In particular, we might want to add on scaling at the same time. These are called similarity transforms. Guess what? It's still a matrix operation. In this case, we're just going to be multiplying the scalar factor s by our rotation matrix. So you already sort of saw just the matrix that does scaling. This is the matrix that does scale plus rotation plus translate all at the same time. And so it looks a lot like basically the matrix that we had before, where we had cosine, negative sine, sine, cosine. But now we have this scalar factor multiplied in. So there's not necessarily an amount that, there's not any constraint sort of on what this component of your matrix has to be. This kind of is accomplishing the scaling and rotation all at once. And then we still have this translation dx dy that happens to our image. And this brings us to the general case of basically all of these transformations. These are all basically affine transformations. So everything that we've talked about so far falls under this category of a 2x3 matrix operation on our coordinate system that we're doing. So full affine transformations basically involve scaling, rotating, translate, and also this shearing operation that you might end up wanting. And basically, each of these are going to be preserving different things in our image. So pop quiz, what does translation preserve? Yep, orientation, angles, size, everything, basically. All it doesn't preserve is position. Euclidean preserves distances. Yep. Similarity. I can't remember. We'll get to the slide in a second. And affine ends up preserving, I think, just parallel lines, basically. So the general affine transformation is just this 2x3 matrix where any of these components can be anything. And we're just going to multiply this matrix by our coordinates that we have. And they can accomplish basically any of these operations, any of this scaling, rotating, translating, or shearing. What happened to my little thing? That's weird. So in general, affine transformations are nice because we can combine them together pretty easily, and we still basically get affine transformations. So say you have this long process that you want to go through with your image where you want to translate it somewhere. Oftentimes you want to translate it to the origin and then rotate it and then translate it back to where it was. And this can be sort of hard to think about. You have to do this translation matrix, and then you have to rotate, and then you have to translate it back, and then maybe you want to do some other stuff with it. In general, we can just combine all of those together. So if you figure out what each individual component matrix is, we can just multiply all of these matrices, all of these transformation matrices together, and the result will still be an affine transformation. And hopefully someone sees some problem with doing this. We just talked about how affine transformations are these 2x3 matrices. So what the heck are we doing here? We're multiplying a 2x3 matrix by a 2x3 matrix by a 2x3 matrix. That's not how matrix operations work. Well, we can just add this row to our matrix transformation. And now they're all 3x3 matrices, and now we can just multiply them together. And in particular, you'll note that when you multiply these matrices together, you still preserve basically the bottom row as being 0, 0, 1. So if you're trying to fill in basically the bottom left component, you end up multiplying 0 times cosine, 0 times sine, plus 1 times 0. As long as these are all affine transformations, they're all going to have 0, 0, 1 in the bottom. So the second sort of the second entry of the bottom row of multiplying any of these together will also be 0, 0, 0. And then sort of the bottom right component will be 0 multiplied by something, 0 multiplied by something, and 1 multiplied by 1. So we'll end up adding basically the same bottom row to multiplying any of these affine transformations together. But that's fine. it's still an affine transformation. Basically, the only interesting thing happening is up in sort of the top 2 by 3 area. And also, when we multiply this matrix by some x bar, we are just multiplying, as sort of the last component that we get as our result. We're multiplying 0 by something, 0 by something, and 1 by 1. So we're actually just calculating x bar prime, where we've added this extra 1 component at the bottom of our coordinate. And that's fine. We can just do this calculation and then ignore it. So this is cool. We have these affine transformations. And any of them can sort of be combined together with any other affine transformation. And we can do all these coordinate system transforms at once. But there's something that we might want to do that is not affine. And this is projective transformations. And affine is any 2 by 3 matrix, but we can imagine basically wanting to go outside of this bound of preserving parallel lines and doing some more interesting transformations between different images. Projective transformations should sort of make sense to you in terms of like if you've ever held a camera and sort of panned it up and down, the lines don't necessarily stay parallel. If you're kind of looking at 2 vertical lines here and then you pan the camera down, the lines go off into space and they start kind of diverging. So you can imagine basically wanting to stitch together images where these parallel lines do not stay parallel, and we need this added potential transformation. So this is not going to be an affine transformation. So to be able to do this new transformation, this homography or perspective transformation, we need another new coordinate system. And in particular, we're going to talk about homogeneous coordinates. And these are useful because they allow us to do this transformation. And in general, they're useful for some other stuff too. But basically, you can think of homogeneous coordinates as encoding every 2D point as a 3-dimensional vector. And what that means is that they're going to be equivalent up to some scaling factor. So a homogeneous coordinate is going to have these components x, y, and w. And what we really care about are x and y as relative to how big w is. So our normalized form of our homogeneous coordinate is when w is equal to 1, then we have basically our real versions of x and y. So if we want to calculate our old coordinate system, sort of our normal 2D coordinates, we have a pretty easy transformation where basically x bar is just going to be x in our homogeneous coordinates divided by the w component. So we're going to divide by w, and you have x squiggly divided by w squiggly, y squiggly divided by w squiggly, and 1 in the bottom. And that gets us back to our x bar coordinate system. But these homogeneous coordinates are nice to work with, and there's some intuition behind kind of why they make sense. This isn't an exact explanation, but basically, remember our little pinhole camera model where we were sort of talking about how cameras work. And basically, it's this projection of 3-dimensional space onto a 2D plane. And this is sort of similar to what we're doing in homogeneous coordinates, where basically points in 3D space are kind of indistinguishable from each other in this projective transformation if they fall along the same vector. And in particular, this is the vector that starts where your aperture is and goes through this image plane. So you can imagine, like, if I take a picture of from right here or something, this microphone might be sort of in the same line as something behind it. And all I will see is kind of this black pixel. And I don't necessarily know just from this single picture if that black pixel corresponds to sort of this point in space or some point in space that's very far away. If I knew some computer vision, I could do some processing on it and maybe figure it out. But basically, points along this vector that sort of stretch out from our focal point will be indistinguishable from each other. And so this is kind of how cameras operate, and this is kind of one start of an intuition for why homogeneous coordinates might be important when we talk about computer vision. And for why this transformation makes sense in particular when we're talking about panoramas. And you guys will be coming back to all of this when we talk about 3D stereo stuff and optical flow stuff. So don't worry, you'll get more of an introduction to kind of these transformations into homogeneous coordinates. But for right now, just kind of keep in mind that this is why this transformation makes sense. So affine transformations were these 2x3 matrices. Homographies are going to be a more general case where we have this 3x3 matrix. And in particular, we're not going to limit the bottom row to be this 0, 0, 1 that we had in the affine transformation. It's going to be a lot more general. And with homographies, we have this weird property where multiplication by a scalar is equivalent. So you can imagine that we have this homography that maps from x to x prime. And if we multiply this whole side of the transformation by some scalar, it's the same as multiplying the result by some scalar. And we already talked about how in homogeneous coordinates, all that matters is basically the direction of the vector, not the scale that corresponds to that vector. So when we end up transforming back to x bar, we're going to divide out by that w component, and basically that scaling factor is going to go away. So this homography transformation in general is equivalent up to some scaling factor. So if you take one homogeneous transformation or one homography and multiply it by a scalar, you still have the same transformation. You haven't actually done anything interesting with it. So it's this 3x3 transformation matrix where we have all of these components. There's no sort of constraint that we put on these components. But again, just remember that basically it's equivalent up to some scaling factor. So a transformation of 3h is the same thing as just the transformation by that initial homography. So how do we use this if we want to actually project a point? The same way that we were using before, except we're going to be in these homogeneous coordinates, where basically we take the point that we're projecting and we do this matrix operation. So x is going to be, our sort of x prime is going to be h00x, h01y, h02w, et cetera, et cetera. We're going to fill in all of these components. And then we're going to divide through on this side by what this w ends up being. And w is just going to be h20x plus h21y plus h22w to get, where'd my little pointer go? To get w prime. And then when we want to sort of calculate basically what x bar prime is, we just take x squiggly prime and divide it by the w prime that we end up calculating. So that's how we kind of use this homography to project a point between these two coordinate systems. And so which one of these coordinate systems is kind of the right one to use? There's a lot of different choices, and there are different situations where you can imagine using these different transforms for different applications. In general, basically, projective transformations will cover any case if you make a pretty strong assumption about the thing that you're taking a picture of. And that assumption is basically that you're taking a picture of some planar surface. So if the thing that you're taking a picture of is like a wall, for example, and you just take a bunch of different pictures of that wall, it actually doesn't matter what you do with your camera. You can sort of move it around in any kind of orientation or angle, et cetera. And all of those images will be translatable back and forth between each other using a projective transformation. Now, why does this make sense for panoramas? Well, when things are like really far away from you, they're basically a wall or something. They're kind of a planar surface. You can imagine that, if all of the things that you're taking a picture of were at infinity, that's basically a planar surface. So all of your transformations are going to be projective between them. So in general, if you make this kind of strong assumption, then we can use this projective transformation. And in practice, there are a bunch of other transformations that people use for panoramas. They sort of map onto these like cylindrical or spherical coordinates and do stuff there. And those are just harder to solve for. So all we're going to talk about is projective. But you can imagine basically like now you understand kind of the general concept of mapping between different coordinate systems using some matrix transformations. You can imagine that mapping to other coordinates probably isn't very hard. You could probably figure out how to do it. So what we want to do is recover the transformation in our panorama so that we can stitch these two images together. So we have these two images, and we have some reason to believe that basically there's some transformation from one image to the other image. And if we just figure out what that transformation is, we can map between them and stitch them together in a panorama. So how hard are these matrices to actually recover? Who wants to give a stab at it? What we're interested in basically is degrees of freedom of these matrices, because that will tell us how hard it is to recover. So for translation, how many degrees of freedom are in this translation matrix? 2. Good. Everyone's got it. What about this rotation and translation matrix? 3. Oh, you guys are on a 4. What about this one? Who said 9? You guys all said 9. You're all wrong. OK, it looks like there's 9. But again, remember that we have this scaling factor that homographies are all equivalent up to. So in practice, you can kind of think of this as having basically, you can normalize a homography by putting a 1 in H22. And that's sort of your transformed back to like some kind of, some kind of true version of that homography. And if you do that, or if you sort of think about basically these are equivalent up to some scalar, what you actually get is homographies have 8 degrees of freedom. But I don't blame you guys for thinking that it's 9, because I just told you about sort of the equivalent up to scalar thing. So yeah, we have a bunch of different transformations, and we have different degrees of freedom of each of these transformations. And we have just a nice little summarization table of the things that each of these transformations are going to preserve. So if we have a transformation, say we think that it's just a simple translation between two images and has 2 degrees of freedom, how many matches in our images do we need to estimate or to sort of calculate what the correct transformation is? How many matches? How many points in each image do we need? Who said something? Just yell it. If you're right, yes, got it. So because basically 1 point is going to have an x and y component, it's going to give you 2 equations, and it's a system of 2 equations and 2 unknowns. So in general, we're going to be solving for all of these just by setting up some equations of these different transformations with our matches, and then estimating this transformation, or just sort of calculating it exactly using these different equations. So we want to figure out what this A is. And if it's a general affine transformation, it'll have 6 degrees of freedom. And we know that we get basically 2 equations with each of these matches. So we'll just need 3 matches to basically calculate our transformation, if it's an affine transformation, between 2 different images. And in particular, basically, when you just do out this matrix transformation, if we say that basically m and n are 2 matches in our coordinate space, then we know our component nx is basically made up of this summation, and ny is made up of this summation. And we can put all of these entries into a new sort of into these new matrices that basically set up this linear system of equations. So in general, we know how to solve linear systems of equations where we have some matrix M and some matrix B, and we want to figure out the A component where we can have MA equal B. And so what we're going to end up doing basically is using these linear equations that we get, put together this matrix M that consists of basically some components of the matches and some 1s and 0s, put together this matrix A, and put together this matrix B, such that when you do this matrix operation, M times A, you get basically this side of the equation. And the weighted sum that basically this row with this A matrix ends up being the match n, and sort of the x component or the y component. And we can put together these matrices such that if we solve this system of equations, we are left with the components of this A matrix, which are just the components of our affine transformation. So in general, we can just sort of take an inverse of M to solve this linear system of equations if we have just sort of exact matches and we have the right number of them. Now, we don't have exact matches. And in particular, we have a lot of matches, and a lot of them are not very good. So we have basically an overdetermined system of linear equations that we want to solve. And we can still do it. And sort of this process still works even if it's overdetermined. And class is out of time. So next time, you will figure out why this works. And then you will figure out why it doesn't work.